We built a LoRa sensor unit. Now we want to measure the LoRa transmitter performance and the power consumption of our unit with simple and cheap methods that a hobbyist can carry out. We covered already a number of interesting topics in our little project. In our overview here, the green check marks indicate the covered hardware and software, and the green monsters indicate where we have made interesting experience and measurements. In case you are interested, please go back to the earlier episodes where this is explained in detail. The red monsters indicate the LoRa measurements that we will carry out in this episode. With the code that we created in the last episode, we were able to activate the deep sleep mode of our ESP32 LoRa board components. We did that stepwise, and we want to know now the effect of these steps in terms of power consumption. Our code also controls the data transmission period, the duty cycle, and the airtime indirectly through the spreading factor. We kept the default value of spreading factor 7. With that default, the LoRa transmitter is active for about 60 milliseconds, what we can find out from the LoRa specifications. In our case, we repeat a transmission periodically every 3 minutes. We can calculate the theoretical duty cycle with 60 milliseconds divided by 180 seconds. The result is 0.033% duty cycle. We want to measure whether our entity works correctly according to our specifications. And finally, we want to measure the actual LoRa transmit power of our board that is working at 866 MHz. This is not an easy one because it requires some RF measurement equipment. But don't worry, we use a do-it-yourself method that you can also realize on your own in case you are interested. The measurements for the board's power consumption can be done with a simple multimeter. But keep in mind that the accuracy will not be the greatest, because our microprocessor boards don't draw a constant current. It is rather bursty and with a lot of short spikes. But anyway, even if not very accurate, the results are giving us a good idea what happens. Of course, it would be better to use an oscilloscope for this, because we could see then the bursts and the spikes with it. Now, let's talk about the measurement results. In the standard mode, our board is drawing about 50 milliamperes, which in theory corresponds then to a runtime of about 60 hours with our 3000 milliampere hours battery. Applying the board's deep sleep configurations with the commands given yields about 15 milliampere average consumption during deep sleep. From our own software code, we can estimate that the active periods will be about 200 milliseconds, where the consumption is the same as in the standard mode. If we neglect the short active periods consumption, this would correspond then to about 200 hours runtime. As I explained already in the last episode, I struggled a bit to find out that the LoRa part of the board needs an extra sleep command. Applying that, I was able to reduce the power consumption to about 8 milliamperes. This would correspond then to 375 hours runtime. I think if we would use an actual low power board, we could even improve that to less than 1 milliampere, and we could reach about 3000 hours of theoretical runtime. Now, in reality, we can only achieve about 80% of the given runtimes for two reasons. First, the current spikes are not the friends of your battery. Together with the internal resistance of the battery, they reduce the efficiency compared to a constant discharge current. And second, the short active periods are not considered in this estimation yet. In case you are interested in more details here, please go back to the earlier episodes where we discussed the dimensioning of a solar powering and batteries. We also provided helpful spreadsheet tools for this. Next, we want to talk about the RF measurements of our LoRa transmitter. And here I have to give you an important warning first. Don't connect strong transmitters directly to a sensor input. It would immediately destroy the sensor. Our AD8318 sensor is rated for 10 dBm input maximum. Since I know that LoRa transmitters can go up to plus 20 dBm, I did my first measurement with a 30 dB RF attenuator in between. I only removed it when I realized that the RF output power of my LoRa boards here is something close to 0 dBm. Now, the AD8318 is a logarithmic RF sensor which is specified from 1 MHz up to 8 GHz. Its output is a DC voltage that is proportional to the received RF power. The output DC voltage is then processed by an Arduino data logger and recorded by a terminal program on the laptop. We use the freeware CoolTerm for this purpose. If you are interested in do-it-yourself such an RF measurement device, I have good news for you. There will be later episodes covering the making of this. Now let's do the RF measurements. We set up the set arrangement with our little RF measurement device and the laptop. We connect our LoRa sensor unit via an RF cable to the measurement device. As mentioned earlier, please be careful here. You better try with an attenuator between the devices first. Next, we adjust our device and start the terminal program which records our measurements. What we expect is a short RF signal that appears periodically every 3 minutes. We can observe this on the LED display with the red hold function, as well as from the numbers on the laptop screen. However, we want to do the measurements for a whole hour, and of course we don't want to read and evaluate this manually. With our terminal program, we can record the readings from the serial interface of our RF measurement device. After the hour, we recorded a text file, which I'm showing you here. In the header of our recorded data, our data logger is always giving us a help menu of its commands and functions. In case of any change of functions or parameters, it is giving us here the current settings. We said that we want to record one measurement per 1000 milliseconds, which is of course 1 second, and we want to record 3600 measurements. And we want to get the peak power values within each second. And we set our duty level to -20 dBm, which is our trigger to indicate the transmitter's activity. Then we get the desired recordings. In our case here, we only look at the first two columns and the last two columns. They are giving us the tracking number of the measurement, the time, the peak value of the received power, and the duty level in the last column. We can import this text file into a spreadsheet. I'm using Excel here, but any other spreadsheet tool would do the job as well. We shape the data a bit so that we get rid of the stuff we do not need. Next, we can apply some simple spreadsheet functions in order to get the desired values. First, we find the maximum of our recorded peak power values. That gives us the maximum transmit power of our LoRa transmitter that we received. Second, we compute the average of our duty cycle column. This is giving us the duty cycle over the whole period. Third, we just count the shots that are bigger than 0. As expected, this is giving us exactly 20 RF shots in 1 hour. Fourth, we calculate the airtime per hour from the number of shots and the duty cycle. And fifth, we calculate the corresponding airtime for a whole day. Now, let us see where we stand with our measurements compared to the specifications that we defined. The data transmit period, the duty cycle and the airtime are really close to our specifications. Very nice. The measurement for the transmit power says 1.23 dBm. I mentioned earlier that I struggled a lot to adjust the transmit power to any other value. However, there was no change at all. Maybe somebody has an idea how to achieve this with my boards. Please let me know in that case. RF power measurements are a bit tricky because you always lose power on every connector or cable. I made an estimation of the losses here for the given frequency in order to better estimate the actual transmit power. With that, I estimate the transmit power to 2.53 dBm, which is about 1.8 milliwatt at the level of the antenna connector. This is a pretty low power, however, as we will see later on, with LoRa we can achieve still a respectable radio range. The summary. We reduced the power consumption to the minimum that was achievable with the given TTGO board. All radio parameters measured were compliant with our specifications. And we measured the actual LoRa transmit power. Hope you enjoyed this episode. The coming episodes will cover the server hardware, software and experiments. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.